Here is one final example of a homomorphism involving groups from this course. Let's take one involving the symmetric group. It's going to take on values either 1 or -1. This one's going to be a little more complicated. Let sigma be a permutation. Write sigma as a product of transpositions, sigma 1 through sigma k. Remember, it's a theorem that it's possible to always do this for some k. Then define sigma n, sig n, this is called the signature, by the way. Define the signature of sigma to be -1 to the k. Now, what should not be obvious is that this is well defined. As you might remember, it's possible for a permutation to factor as a product of two cycles in more than one way, and in fact, with different numbers of factors. It's not like integers where the number of factors in the prime factorization is always the same. But the theorem we did see was that if you found another such factorization where tau 1 through tau m are also transpositions, then k and m were congruent mod 2. Which means, in some sense, that m is equal to k plus an integer times q. So then -1 to the m is -1 to the k plus 2q. It's -1 to the k times -1 to the 2q, which is -1 to the k times -1 squared to the q. Oh look, that's just 1. So you see that -1 to the k is equal to -1 to the m. So it doesn't matter what factorization into transpositions you take, you're either always going to get something positive or something negative. In other words, you're either always going to get a factorization of odd length, in which case you get -1, or a factorization with even length, in which case you get +1. Which actually gives an alternative way to define this. Sigma is an odd permutation. 1 if sigma is even. But the definition of odd and even is exactly this definition. Of course, I still need to show that it is a homomorphism, but assuming that it is, the kernel of the signature are those permutations where the signature is the identity element, which, based on what we just saw, means they're even permutations, which means you get the alternating group. So in particular, this gives an alternative proof that the alternating group is a normal subgroup of Sn. So why is the signature function a homomorphism? Well, let's figure it out. Let sigma and tau be two permutations. What do I need to check? I need to check what happens when you compute the signature of the product. Well, let sigma factor as sigma 1 through sigma k. Tau factor is tau 1 through tau m. These are all transpositions. And what's the signature of this product? Well, it's the signature of this one, so it's -1. The point is sigma 1 through sigma k times tau 1 through tau m is in fact a factorization of sigma times tau into transpositions as well. So you have -1 to the k plus m, which is -1 to the k, times -1 to the m, which is the signature of sigma, times the signature of tau. So we see that the signature function is a homomorphism. And since it's a new one, I will at least point out 2 other places in mathematics where I have seen it. Although this part is optional, so you can end the video at this point. So the first application I've seen is in linear algebra. So you let A be an n by n matrix. Then you can write the determinant of A as a summation over all permutations in Sn. The signature of that permutation times A sub 1 sigma 1, A2 sigma 2, dot 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 A n sigma n. So what this is doing is for each permutation, here I'll do n equals 3. You're looking at exactly 1 entry in each row and column corresponding to that permutation in this matrix, and you're multiplying exactly those entries together. And then you're multiplying that by some plus or minus sign, and you're summing that together, and that's a closed formula for the determinant. So this is one way to prove that the determinant is actually well defined, because it has exactly one formula like this. Although in terms of computational complexity, it's a complicated formula because it involves n factorial terms. But I do know plenty of cases where this formula ends up being useful for doing certain proofs. The other fact I know about the signature that's kind of neat is another way to calculate it. Suppose you write sigma in one-line notation. You know, the notation we tend to avoid in this class. Then the signature is also -1 to something called the number of inversions, where the inversions are the number of ordered pairs where I is less than j and sigma I is greater than sigma j. So for instance, if I take a permutation 1, 3, 4, 5, 2, let's see if I can't count the number of inversions. So basically I'm looking for pairs where the larger number occurs earlier than the smaller number. So for instance, I see 3, 2. So that's position 2, 5 is an inversion. Similarly, I see 4, 2, so that's positions 3 and 5. And 5, 2, that's positions 4 and 5. So there's 3 inversions right there for this permutation. And that's really it. So this permutation has 3 inversions, which means that this permutation is odd. So congratulations, I've now actually given you a quick method using one-line notation to determine if a permutation is even or odd without looking at the cycle type or having to factor into 2 cycles. I also know a trick for when you have it in cycle notation without having to factor into 2 cycles as well. Granted, you're not allowed to use that trick as an answer because you don't actually know the proof for why this is.